Hi everybody, welcome back. In this video we're going to continue talking about randomized control trials and specifically looking at an example of a randomized control trial in health insurance market back in the 70s. And so in the last video, recall that we were looking at what randomized control trials do, and we ended up with this little figure here where we have an underlying population, and this population has all sorts of observable and unobservable characteristics. And if we combine a random assignment with the law of large numbers so that we draw a large enough random sample from the population to be in the treatment group and a large enough random sample to be in the control group, both of these groups are going to be similar to the underlying population, even if the population is really big and you have samples of they can still be relatively small, but they need to be big enough for the law of large numbers to kick in. These treatment group and control group, they're going to look exactly the same, not only to the underlying population, but they're going to look exactly the same, or at least not statistically different from each other, both in observable and unobservable ways. The only difference between these two is going to be one has a treatment and one doesn't. Okay, and so that's the beauty of randomized control trials, and that's what we're going to see in practice here with random assignment in health insurance markets. So, random assignment in health insurance, HI health insurance markets. Couple examples in the past. The main one we're going to be discussing in this video is the RAND health insurance. Let's do the RAND health insurance experiment, which I'll just abbreviate from now on as RAND HIE. And another one called the Oregon Health Plan Lottery. Oregon Health Plan Lottery. OHP. Okay, and sometimes I might just refer to the RAND HIE health insurance experiment as HIE. Okay, so let's talk about what that was, the RAND health insurance experiment. It was run from 1974 to 1982, and it was one of the most influential social experiments in history. One of the most influential social experiments in history. How it worked was there were about 4,000 people, 58 people, aged 14 to 61, who had no Medicare. So they did not have health insurance. And they were randomly assigned into insurance plans. Okay, and here's what those plans included. The first one was catastrophic insurance, which here we're kind of equating this to essentially almost no insurance, because it's only going to kick in if there are absolute catastrophes. We have a deductible plan And the deductible plan offers some coverage, but expenses on the individual. Some coverage, but most expenses, especially at the beginning until they've reached their deductible, are on the individual. Then we had coinsurance, where the expenses are split between the individual and the insurer. And finally, some people received free health insurance. So they got the policy, but they didn't have to pay anything. Okay, and so now that we have some treatment groups, the first thing we have to do when we have a randomized controlled trial, a random assignment, is that after you randomize the people into treatment and control groups, you have to check for balance. So let's write that down and talk about what that means. After randomizing people into treatment and control groups, I'm going to use our abbreviation, treatment and control groups, we must check for balance. And what we mean here is essentially, do the treatment and control groups actually look similar? Do the treatment and control groups actually look similar? And the way that we're going to do that is compare average differences across observable characteristics. Compare average differences across observable characteristics. And essentially, if we find that there's no statistically significant difference between what's observable between these groups of people, then it's going to be highly likely that their unobservable differences are going to be the same too. And so we're going to do this every time. Always do this when you are estimating causal effects. Always do this when you are estimating causal effects. Okay, so next we ask ourselves, how do we know if differences in means or averages are statistically significant? How do we know that differences in means, which are averages, are statistically significant? And essentially what we're asking there is, how do we know that a difference in the average between two groups is not simply due to chance? And the answer to that question is that we look at the standard errors. The standard errors of the differences. which are estimated, and we're going to abbreviate standard errors as SEs, or the standard error being SE. This should be familiar from statistics, but remember that standard errors summarize the variability in an estimate due to random sampling. Standard errors summarize the variability in an estimate due to random sampling. Okay, and just as a quick refresher there, standard errors, remember, if we had some probability distribution and we had an estimate of the difference between two groups, and so this distribution is the difference. So we could check to see if this is the true or the population distribution. The mean there is going to be mu. That's the population mean. And the variance, which is the variation in the data from the mean, that's the standard deviation. Okay. It's unless we survey every single person for the population we're interested in, which just isn't feasible, we're going to take a population of people. And when we do that, what's going to happen is we may end up with we will almost surely end up with a different distribution. Let's do it like this. That'll work. So our sample distribution is going to be a little off. Ideally, we're going to want the means to be the same. Let's suppose this is some outcome x that we're interested in. X bar is the sample mean. Ideally, we're going to hope that we have an estimate where the larger the sample size is, the more likely that we're going to approach the population mean. But we also see that we have a bit of a tighter distribution of data. The standard deviation is larger in the population than it is the variation in the sample. And the variation in the sample is the standard error. So standard deviation is the variation for the population. Standard error is the variation for the sample. Okay, and so again, we want to estimate a distribution as close as possible to the true distribution, and then with that law of large numbers and what we call the central limit theorem, the larger the sample size is, the more, and given the proper estimator, the closer we're going to get to that underlying population estimate. Okay, and so anyway, that's that idea of a standard error. And as a rule of thumb, when we're looking at standard errors, we can use a rule of thumb to tell whether or not a difference can be attributed to chance or not. So that's our standard error rule of thumb. And what we have here is when an absolute difference in sample averages is smaller than about 2 standard errors. The difference can be attributed to chance. So when it's smaller than about 2 standard errors, the difference can be attributed to chance. And the number 2 there, it's kind of convenient with a simple t-test from back in statistics. 95% confidence interval on a difference in means is going to be 1.96. 99% confidence interval is going to be around 2.3 or so. And so 2 standard errors is going to give us a high likelihood that the difference in these two samples can be attributed to chance if that's smaller than 2 standard errors. So when the absolute difference, I'm going to actually just copy this. When the absolute difference is larger, let's do that. There we go. So if the absolute difference is larger than 2 standard errors, the difference can be said to be statistically significant. Okay, that is, it's unlikely the difference is due to chance. Okay, and so let's look at a quick example of that. We're going to do an example here, and then we're going to see how this plays out in the Rand health insurance experiment. So in one of the previous videos, I showed table 1.1 in our book, Mastering Metrics. Let's get a good line. Okay, and there were a number of variables there, but let's just look at the family income variable. And we look at family income among those with health insurance, those with no health insurance, and the difference. And so in the table, we see that the people with health insurance have an average family income of $106,467. Those without health insurance have an average income of $45,656. The difference between those two being $60,810. And underneath the difference, we see in parentheses the number, and these are in the same units. So $1,355. Okay, and in the bottom of the table, you'll see something like standard errors in parentheses. Okay, and so now what we can do is take our rule of thumb and compare these two family incomes with and without health insurance to see, it looks like they are very different from each other, but we can't be sure of that until we've run the statistical tests. And so the difference in means is 60,810. The estimated standard error, 1,355. And so 2 times the standard error is just 2 times 1,355 for 2,710. And now, again, we use this as our rule of thumb to see if 2 times the standard error is larger or smaller than the absolute value of the difference. So the difference, we want to check if it's greater than, less than, or equal to 2 times the standard error. And in this case, the difference is a positive number. The reason we use absolute value is because standard errors are always positive. But 60,810 is greater than 2,710. And so because that comes back to our rule of thumb here, if the absolute difference is larger than about 2 standard errors, the difference is said to be statistically significant. So we can say with somewhere between 95 and 99% certainty that the people with health insurance do actually have higher incomes with a statistically significant effect or difference. They do have higher incomes than the people without health insurance. So summarize that here. The difference in family incomes between those with and those without health insurance is statistically significant. Difference in family income between those with and without health insurance is statistically significant. And if you go to table 1, you'll see that that's true in so many of the other variables in table 1. And what that's also then telling us is that, okay, because we have statistically significant differences, this is not a random sample. Okay, remember, table 1 was just observational data. Table 1 didn't come from a randomized controlled trial or some type of random assignment. We just looked at people with insurance, without insurance. We saw that the people with insurance had higher levels of health, but we also saw that everything else was not equal. We didn't have that ceteris paribus assumption holding, and the people with health insurance also have statistically significantly higher incomes, higher education levels, higher levels of employment, and so on and so forth. So because this holds for other variables, there's likely to be selection bias. Okay, and because this holds for other observable variables, that means it also probably holds for unobservable variables. Okay, and so we don't have a random sample, so it's inappropriate to try to look at the difference in means in health outcomes between those with insurance and those without insurance. That provides you no information about the effect of health insurance on health because you're not comparing similar groups. And so now that we have this this idea of standard errors and the comparison of differences under our belts, in the next video, what I'm going to do is jump into that RAND health insurance experiment. We're going to look at the randomization into the different insurance plans, and then we're going to see how does health insurance affect health. So we're going to be looking at a general health index, cholesterol, blood pressure, and so on and so forth. So stay tuned for that in the next video. I'll see you then. Thanks.